So here we go with the actual grid that kind of matches the dot diagrams you did for homework. So we're going to try and follow these rules over here. So we add the valence electrons. Carbon is 4. I is iodine. Iodine has 7 valence electrons. So hiding back here is our periodic table. I'll just remind you about that. Carbon has 4 valence electrons. It's hard to keep all these tiles together. So carbon's got 4, and iodine has 7. See, it's in the 7th column. So since carbon has 4, iodine has 7, we're going to write down 7 down here. Oops. 4, and then 7. But there are 4 atoms of iodine. See that little 4 right there? So you got to multiply this one by 4. So 7 times 4 is 28. Plus these 4, you've got a total of 32 valence electrons. So now we're ready to draw our skeleton structure. What goes in the middle would be carbon, because it's closer to the middle of the periodic table. And then you put your iodines out around it. Of the 32, I now have 8 in the picture. So I'm going to take away 8 of them because there are 4 bonds, and each bond counts as 2 electrons. So 32 minus 8 is 24. All right, so 24 dots to put in. 1, 2, 3, 4. One there. 5, 6. 1, 2, 3, 4, 5, 6. That's 12 of the 24. Remember we had 24. Oops. So 24, oops. Okay, so here's 6 more. That's 18 of the 24, and then like that. So there's your 24 dots. Does everything have 8 around it? Yes. 2, 4, 6, 8. 2, 4, 6, 8. That is a line right there. I'm hovering too much, and then it makes my pen act weird. So 2, 4, 6, 8 here. And 2, 4, 6, 8 around that. 8 around the carbon. I just counted them. 2, 4, 6, 8 around the iodine. 2, 4, 6, 8 around that iodine. Everything's good. Okay, so the domains around the center, you see 1. I'll circle them. Oops. So 1, 2, 3, 4. So there's 4 domains. On your electron domain geometry sheet, let me pull that up real quick. You can see 4 domains is tetrahedral. All of these domains are shared, so the molecule geometry is tetrahedral also, and the bond angles are 109.5. All right, so our electron domain geometry we said was tetrahedral. The molecular geometry is tetrahedral, and the bond angle is 109.5. Now the type of bond, polar or nonpolar, you have to look at electronegativities. So let's pull up our electronegativity chart, which I have sitting on the sidelines here. So here we go, the electronegativity chart. We're looking at carbon compared to iodine. So 2.5, 2.7. We would say each one of these bonds is nonpolar because the difference is only 0.2. Okay, so we'd say that is nonpolar. Ultimately, that won't make a difference in our determination of polar or nonpolar because of this. So you got your iodine, or carbon's here. It's going to kind of shape up like this. I'll put a carbon as an atom symbol, just put dots for the iodines. Okay, between iodine and carbon, they're pretty much evenly sharing these electrons, but if they share unevenly at all, the electrons would move in the, the electrons would move in the direction of the more electronegative element, which would be iodine. So it'd go up toward the iodine, down in this direction, back that way, over here. So they're all equidistant from each other, all pulling equally, so the molecule will be nonpolar in P. Now, even if this was like fluorine or something, the molecule is still nonpolar because these molecules are going to all cancel out. I mean, these arrows are all going to cancel each other out. Okay, now we're going to try SeO2. Okay. Oh, incidentally, This answer right here is based on the point, using 0.2 as a reference point. So that I used 0 to 0.2 on this sheet when I made it. So based on that, this would be polar. Ultimately, what we care about is this, and that is this molecule is nonpolar. All right, SeO2. Pull out your periodic table, and you'll know, you'll find it over here on this screen that you can't see. I come over here. The selenium is right here, Se. So it's got 6 electrons, and it's further closer toward the middle than oxygen is. So we put selenium in the middle of our dot diagram. And then we'll put oxygen here, oxygen there. All right, add our valence electrons. There were 6. Do you remember it's in the 6th column? Plus 6 times 2. So we have a total of 18 valence electrons. This is like the one we did up above. Are you noticing that in the previous video? So you're going to take away 4, and that gives you 14 dots to put in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm out of dots. I still need 2 more right here. So I am 2 short. Like going back to these rules, if we're 2 short, we add 1 double bond. So I'm going to just redraw the picture down here for the sake of space with a double bond. Now I subtract 6 instead of 4 because, so take away 6, it gives me 12 because now I've got 3 bonds in the picture. So that gives me 12 loose dots instead of 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I think I put 8 around everything. 1, 2, 3, 4, 5, 6, 7, 8. Around the sulfur, 1, 2, 3, 4, 5, 6, 7, 8. Around this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. So everything has 8. That's our dot diagram. Skip to domains. How many domains do you see? 1, 2, 3 domains. So the electron geometry for 3 domains, I'll pull that sheet over for you. That's this one. So 3 domains, trigonal planar. In this case, again, like in the previous video, 2 are shared domains and 1's unshared, and the bonds will be 120. So the 2 shared domains are this one, and that's an unshared domain. So the electron domain geometry is trigonal planar. But the molecular geometry will be bent because of the 2 shared and 1 unshared. Bond angle is still about 120. All right, type of bond. We need to look up electronegativities. Let's go back to the electronegativity table. Selenium is 2.6. Oxygen is 3.5. So that difference is 0.9. So I'll write the difference down is 0.9. 0.9 is greater than or equal to 0.4 for sure. So that means this bond is polar. Now let's go to the 3D structure. Remember these electrons repel? Oops. So electrons are going to put, when we draw it, it's going, since they repel right here, that's going to bend this molecule down. And that's what I mean by bent. So it'll look like this kind of, and there'll be a double bond on one side. All right, so now which way would the electrons move? They would move toward the more electronegative element. Was that the O or was that the Se? Just now noticing I forgot to put the E on that. There's an E down there. All right, so the electron is going to go toward the O because it's more electronegative. So that way and this way. So will these arrows cancel? No. So that means the molecule is polar. Okay, and just one last point. The actual molecules, what they look like. I have the pictures over here. Like this. So the first one was the tetrahedral, and it looks like this in 3 dimensions. So you see that arrows would all cancel no matter how big the outside electronegativity is. The next one, the SO2 or SeO2, looks like this, where you got an unshared pair of electrons here. This is the Se, this is the O. The electrons go toward the O. It's more negative down there. So the electrons are sliding this way, and the arrows do not cancel each other out. So the molecule is polar. All right, that would be the end of this little video.